quite a good. We have quite a good participation at this online seminar. I welcome the speaker, Tomasz Limisiewicz, and I think we can start right now. So, Tomasz, the floor is yours.
Yeah, thank you for introduction. So today probably everyone knows me. I'm studying on ÚFAL, but today I'm connecting from Jerusalem, which is very cold today. It's a few degrees colder than Prague today, and also snow was forecasted for tomorrow, but hopefully it would come. Okay, so let me start. So I'll be talking about interpreting the neural networks, and which are used for natural language processing. So I'll start by providing some background. So the topic is very, I would say, developing. So there are no strict definitions yet, especially when we talk about interpretability. The definition which I found and I find very accurate is that interpretability is the degree to which we can understand the cause of the decision of the model. I would make it a bit broader. I would tell that we also want to not only understand the cause of decision, but also how this causal string, so how this decision was reached. So not only the main causes, but also how this causality link was developed in the model. We'll talk mostly about black box models, that are models which does not reveal their internal mechanism. So of course, based on those two definitions, we can observe that black box model will be quite poor in matter of interpretability. So some motivation. This slide, maybe you know from the presentation that was almost a year and a half ago. So one good thing is that our motivation don't change, but we have new methods, new models, and new findings. So basically, in main motivation of my work and also other people who work on interpretability at ÚFAL and in other places, is that we observed that recently many of NLP tasks, of linguistics tasks, are solved by deep neural networks. We know that those networks learn some patterns that are presented to them in the data, and somehow they can approximate the functions of the language. Unfortunately, even though those models often are very accurate in the task we give them, they're all black boxes. So it's very hard to interpret and know how do they work. So we try to open this black box and look into those models. And a few of the interesting questions we can ask is, firstly, the basic one, how do they work? What abstraction can we observe in them? There's interesting theoretical part to it, because you want to compare how those models understand some linguistic phenomena and how does it compare to their understanding of experts, of linguists, whether do they go in line with the linguistic annotations, or do they invent some other sorts of annotations or understanding. And last but not least, I think that interpretation can be very useful in improving the models. Seeing when what attributes do they lack, and how can we improve in those fields. This is more visual motivations. So I provided some figures and some real task when the interpretation can help us. So on the left, we see a model which was developed in University of Washington, which not only can answer the questions, but only can find the text, parts of the text which are important for the answer. And also what is even more interesting, it can control or change the text in way when the answer changes. So we can identify which part of the text are important for the model. There are also many harmful functions that we can find in the model. For instance, biases, which are learned for large corpora, but we don't really want the model to exhibit. For instance, gender bias, when we see that some sort of words, especially here, the doctor, is connected with one gender. Even in English, it's not denoted in the sentence. And it manifests itself in translation. When we translate to the language which denotes gender in nouns, we see that the doctor tends to be translated to male form. And here in this example, we see that it's again goes against the facts stated in the sentence because we have pronoun, which is female. And even though the model, the translation is wrong. Also, there are some funny examples, like recently I advertised my talk, and I saw that in translation provided by Facebook, the robot emoji was translated to word handsome in English from Polish. Actually, Stanek, maybe he's here, pointed it to me, and I find it kind of funny because it was also an invitation for this talk. And when I talk about interpreting the models, and we see this very intriguing behavior of translation model. Okay, so short outline of this presentation. So first, the part I already started, which is just introduction and what do we mean when we say about interpretability. Then I will focus more on one kind of interpretability methods, which is probing. I will follow with our results when we propose specific methods in line with probing, called orthogonal probes, which offers good insight into representations of the model. And we also talk about how the base of finding interpretations, how we can improve the models. So how we can control those harmful biases or harmful behaviors of the models. And I will conclude by shortly speaking how those methods are imperfect and of their limitations, and what we should consider when using any of those techniques. But first, I want to a bit clarify the terminology. It's mostly terminology of this presentation, because when I talk, I usually use some words, but usually those are just shortcuts, because already I want to present only some kind of subfield of a subfield. So it's there are some very specific terms which may mean something else to me and someone who doesn't work in this field. So first, when I talk about neural network, so we'll focus mostly on very specific models, mainly transformer-based models, so these most recent ones, and mainly those which are large language models. And specifically, if I don't specify it, usually I will have in mind BERT, which is one of very popular neural networks and language models used, its representations are used in many of language processing tasks. Then I will talk a lot about embeddings. And in this context, I will talk about embeddings as the also internal representations of the model. So just for introduction, BERT has multiple layers. It's multi-layer neural network, and output of each layer is vector, which is assigned to some word. It's a simplification, but we can say that for each word, each layer has some vector representation of each word, and then its representation is fed to another layer. It's again processed, and after 12 or 20 layers, we have an output of the model. And when I talk about representation, I will talk about those representations of those vectors, which could be assigned to words. But also in some cases, I will talk about attention weights. So those are even inner parts of those layers. But mostly I'll focus on those vectors, so embeddings. So each embeddings we can think is assigned to specific word in the sentence we provide to BERT. So I just want to note that there are multiple techniques to interpret the neural networks. And here I have just a subset of them. But during this talk, I will mainly focus on one of those, which is probing neural networks. So I just want to emphasize that we have much more tools that I will present, and there are many approaches. We also work here, but just for this talk, I will go specifically into the details of this one method, which is called probing. So let's go into probes. So the basic settings of probing is the idea that we can take the pre-trained model, so let's say BERT or any other language model, or could be also translation model, so something that was trained on large corpora, and then add very simple layer. It could be also neural net layer that will take already existing representations of this model, and we want to train this simple layer on some additional task. For instance, we take pre-trained language model, and then we ask how well this language model represents morphology. So for instance, we can ask this model to provide us part of speech tags. So basically, we freeze the model, so we won't change its weight. At a very tiny, thin layer, just one layer, classifier layer, and train it to predict part of speech tags. And the idea behind probing is that the higher accuracy on this additional task is, on this downstream task is, we can infer the better model represents or encodes this property, because we don't want to add any more parameters or change parameters. Or yeah, we need to add some parameters, but the fewer the better. And we want to ask the model whether it understands or it encodes, maybe it's a better word, this specific task. So I talk about probing for probing classifiers, which are, I think, the most popular ways of probing. But there's also more interesting or more sophisticated probes. For instance, when we want, we can probe for structures. So just as a primer for next slide, I just show how the syntactic trees looks like. And it's to describe another setting, which is syntax or structure probing, where we don't only want to classify the tags for each of the words, but we want to take whole structure which can be annotated for a sentence, which can be, for instance, a syntactic tree, dependency tree, for instance. There are basically two main approaches. One is edge probing, when we take pairs of words and we ask the model whether there exists the edge in dependency trees between them. So this binary probe, which outputs only 0 and 1s. 1s if there is edge, 0s if there is none. Another, I think, very interesting approach is structure probing. When we take the embeddings, so the vectors of the whole sentence, and we can treat it somehow as a cloud of points. Then we want to project these points in a specific way. In this projection, we want to have one property: the distance between projected points should approximate the distances in a syntactic tree. So we can formulate it as linear projections of the vectors to another space when the basic measure of distance, so Euclidean distance, or just approximates some sort of linguistically linguistical property. So in this case, the distance between words in a syntactic tree. And this approach actually gave quite good results in parsing. If we took those distances between trees, we connected the closest closest vectors in this measure, we could retrieve the syntactic trees with high accuracy. Here are visualizations of those two approaches. On the left, upper left, we see just a classifier probe. We take a sentence, and for each word, we assigned a part-of-speech tag. Then we have edge probe, so we take pair of words, and we ask the probe whether there is an edge between them. We can also ask about label of this edge. And here we have a structure probe. So, So we have a matrix, and each element of this matrix represents the distance between two words. And then we train probe to operate on vectors and approximate this distance matrix. So there were a few interesting things discovered with the probes. One is that different parts of the networks tend to specialize in different linguistic properties. So Tini et al. In 2019 showed that the first layers which are the closest to the input specialize in morphology, then syntax and semantics, so more high-level features. And this kind of features is similar to the way that classical NLP pipeline before neural networks worked. So first we have morphology tagger, then parser, and then we could build upon that. So there is some similarity in the way that the networks solve those tasks. So there is also another leg of probing where we don't only want to see which linguistic property is encoded in the representation, but we also want to find the specific subspace of the representation. So only take some dimensions of the representations which encode some kind of linguistic feature. And there were recently a few papers about it, and also a few of us were at recent reading group where I discussed those papers. So those could be familiar to you. So the basic idea is that we don't only want to see whether there is some linguistic property encoded, but also find the specific part of the representation when we can find this specific linguistic feature. So here I want to make the first break. So are there any questions to the introduction and the first part of the talk and the background? Maybe I can ask if, do you hear me if I didn't lose connection? Simply.
Yeah, there is one question, Lukasz and Dominic.
Oh, so two questions, right?
Yeah.
Oh, sorry, that was not a question. That was just marking that we are in connection with the Sorry for that. Yeah.
Well,
so
same here. But now that actually I have taken unmuted myself, I do have a quick question. So you're just looking at syntactic properties in that probing, or are you also looking at vocabulary?
So this will be in the second part of the talk.
Thanks.
So.
Okay, so just continue.
Yeah, I will continue, and in next few slides, I will answer your questions. So in our work, so this is the work from the last year from ACL, we continue this approach of Hewitt and Manning. So we still want to perform structure probing. So we are interested in structures encoded in the representations. And yeah, already I can answer the question. We add new structures. So not only the dependency trees, which were used by Hewitt and Manning, but we also get hypernymy hierarchies from WordNet, where we can find also similar trees, but now we want to count the number of edges in this hypernymy tree. So if the one word is hypernym of another, it's only distance 1, and the further we are apart in this tree, the longer is this distance. So it's very similar, but it's linguistic lexical structure. And in this work, I will show that we can find very interesting relationship between those lexical and syntactic informations encoded in BERT's embedding. So we will show that it's possible to actually decompose those two representations and find the separate subspaces of the representations which encode those two. So once again, about the approach of Hewitt and Manning, I want to repeat it because it's very crucial also to this work. So they took pairs of the embeddings, projected them with just linear transformation, and they had this property that in a projected space, just Euclidean distance between those embeddings approximated the distance in a syntactic tree. Also, they have another task that I didn't mention before. They also just took one embedding, also projected it, computed the length of this projected embedding, and wanted to approximate the depth of the tree in a tree of this word. And depth is just the distance between this word and a root. So in this task, we also need to know where root is. So based on those two tasks, we can retrieve whole directed dependency tree. So just with probing, we can perform actual parsing. So as I mentioned before, they work on dependency trees. So it's shown here. I think I don't need to really explain that this annotations. It comes from universal dependencies. Then we also add additional task, which is lexical hypernymy. So we take pair of words and count number of edges between them in hypernymy trees, which are in word nets. So it's important to note that there are two trees in word nets. One is for nouns, one is for verbs, and they all have one root. So which is, I think, called just entity. So we can find the distance between each pair of nouns and each pair of verbs. Of course, if they're present in WordNet. We also introduce a few baseline structures which are not really linguistically motivated, but also could be interesting as baselines. So one is just positional structure, which is just right branching chain. So here we assume that just first word is a root, and then we have connection between one and the next word. And we also wanted to see whether those probe memorize the trees. So whether if we introduce some not linguistically or in any other way motivated structure, will we be able to probe for it? And for that, we introduce, we just sample a random tree for a sentence. Okay, the third time and last time, I come back to Hewitt and Manning approach. So now it's in visual way. So as I told before, we take embeddings and we linear transform them. Mathematically, linear transformation is just multiplication by a matrix to get projection. So we can really change a shape of the embedding clouds. In our approach, we change this linear transformation, and specifically we decompose it in two parts. So first is orthogonal transformation, which first rotates this cloud of the embeddings. And the second is scaling vector, which scales specific dimension in this rotated space. And why do we do so? So it's for getting better interpretation. So with scaling vector, we can check the magnitudes of those elements of those vectors. And the idea is that if the magnitude, so if we have high value in the scaling vector or very low negative value, we can see that this particular dimension is needed to in those output projection. So this dimensions is where this linguistic information is encoded. And we can then analyze those scaling vectors elements to see where specific linguistic information is encoded in the embedding space. Another benefit of this approach is that we can probe for multiple tasks by once. So we can take just embeddings, then rotate them and use two scaling vectors. So find some dimensions that are important for one task and another dimensions that are important for another task. And what's even more interesting, we can then compare the elements of the loadings in those scaling vectors and see whether similar dimensions are needed for two different tasks. In our experiments, we observed that especially for the syntactic and lexical structures, different dimensions are important. And maybe what I should say even before, that only small subset of dimensions is relevant. The most dimensions in those scanning vectors just converge to 0. So we can really identify some small subspace of the embeddings which encode specific linguistic information. And especially for lexical and syntactic, for example, dependency structures, we saw two completely separate subspaces without any overlap of the dimensions. So therefore, we could say that those two structures were encoded in different subspaces, which are also orthogonal to each other of the Baird's representations. It's important to say that we observed this behavior in this specific figure is from the layer 16 of Baird, but we see similar behavior in most middle layers of Baird. First, it's less pronounced, so we see some overlap. Then basically from second almost to the last, we see that we don't see much overlap between those two informations in the scanning vectors. The exception is the last layer, where all the information seems to be mixed together. And we think it's because this is the layer which is mostly responsible to encode the information needed to perform its basic task. So maybe it's less relevant to probe for some other linguistic features. Also, from other parts, other pair of tasks, we see that also positional probe, so which probes for this right branching chain, is also orthogonal. We don't see overlap with lexical information in the representations. It was a bit expected because usually positional task is quite, in some ways, similar to syntactic trees. In many cases, just trees are just chains, especially in English. Here's the same results, but here in numerical form. So if you weren't convinced by the histograms of the dimensions, which maybe could be a bit convoluted, we computed the number of overlapping dimensions in pairs of the scanning vectors. And it confirms that for those syntactic and lexical scanning vectors, there is no overlap. So we discover completely different subspaces of the embedding space. And it's similar for positional and lexical probes. What is also visible here, the number of the dimensions selected for each of the tasks. So it varies from 14 to about a bit less than 300. We just tell that in BERT we have more than 1,000 dimensions. What is relevant that those highest numbers are for randomly sampled trees. So in this case, we really need to memorize them in the representation. So that's why the probes tends to be very greedy in terms of dimensions. Okay, here I have summary of this work, and also here I wanted to pause for a bit and wait if you have any questions. I think it's maybe most complicated, but also the most important part of this talk, because then I will just build upon this. So if you don't feel completely lost and want to ask about something, I'd love to explain.
Dominic, Lukasz, I think I saw your hand.
Yes, well, I just want to make sure that, did you want to finish the summary first, or did you want me to ask the question now?
Yeah, it's just you can ask now.
Yeah, and sorry, I can have maybe a question a little bit on the confuse spectrum, but I just wanted to wanted to sort of check, because you started talking about embeddings in the second part, but obviously the embeddings are just an input into the trained neural network model, if I sort of understand that process correctly. So are you looking in different ways in both, or just the embeddings, or where's the, maybe I sort of missed that a little bit somewhere.
Yeah, so I tried to say it in the beginning. So I use some kind of shortcuts, like language shortcuts. So when I talk embeddings, I talk about any kinds of vector representation which can be found in the model. So it could be embeddings on 6 layer, for instance, in BERT, which usually are not called embeddings, but I don't want to use representation because sometimes it can be also attention weight. So that's why I just call them embeddings.
Perfectly clear. Thank you.
Okay, thank you.
I don't see any hand. Oh yeah, Wojciech Swatek. Yeah, please.
Thank you for an interesting talk. I'm the linguist, so I will have a rather generic question. Actually, it's 2 questions in a way. First, regarding the explainability of linguistic reasoning, I'm just asking myself when, in which situation this is critical. For example, there are many applications of machine learning where the justification of the decision of a system is really even safety critical or legally important and so on. I'm just wondering, for example, when having an output of a translator, language translator, when is it really critical for me to know why something is well translated, or what is the reason of the source of the problem? And the second actually related question, you can this kind of pro-based explanation can show which part of the, say, linguistic pipeline or a linguistic component which is hidden inside this black box is responsible for example, for the output. But is it sufficient for me to know where is actually the trouble? If I know that, for example, the system is not, or the embedding is not very strong in determining the dependency structure, doesn't help me to answer my questions about, for example, the translation output?
So I would say that like this work is mainly theoretical. So we wanted to see like, yeah, I think like the main outcome here was like to see that we can decompose in this way different types of linguistic features, and we can find some parts of the representation which are responsible of encoding them. And I think if we want to apply it, maybe it's like wouldn't have many applications to just do so theoretical features or signals or information. Actually, yeah, to be clear, it's like not the end of the talk. Like I have also another example when it's like could be more applied when we have more real signals we want to decompose, and we really want to remove like some sort of biases. So I will also talk a bit about that. But like basically in this linguistic approach, I think in lexical, in syntax, yeah, I think it's maybe interesting, but I wouldn't look for very like easy to apply methods when we could bring like easy improvements of the models. So it's like, I think it's more theoretical that we can find some subspaces and we can divide it. We can do like play with it a bit. For instance, get like representation without syntax and think like maybe this will create the words which are or like only with syntax and like which are syntactically correct but doesn't make any sense. So this could be like the outcome of such models, but I don't see really like easy applications of that.
Well, actually, something that just came to my mind. If you have a different kinds of data you want to apply this approach on, you can perhaps let's say if there are texts which really exhibit complex dependency structures, and there are, for example, short texts which don't, right? So this may influence the choice of a transformer model. If you don't need actually dealing with complex dependency structures, it doesn't harm if you use a model that's not strong in dependencies, for example. Just an immediate idea.
Yeah, that could be, but like here it's like just maybe arguments for probing, but maybe not like this interesting part when we want to really find a part. So maybe in this way it's like not that much relevant. But yeah, I would talk. So how much time do I have? Because I have like two more works to present, and maybe I will focus based on interests to one or another.
I think you still have 20 minutes or something of that sort.
20 minutes. Okay, so maybe I will go shortly through the next one, and maybe talk a bit more about work in progress if I had this question. So this was one paper, and we done a continuation when we wanted also to apply this method for multiple languages. And we also probed for syntactic and lexical information in this time multilingual BERT, and we extended our analysis to 9 languages. And here we were more interested in answering the specific question, like how similar are the representations across different languages? So this question already appeared before. There are few hypotheses about this phenomenon. So we could assume that that in multilingual model, the language information is encoded in the same way, in the same place of the representations across different languages, which I'd say uniform representation, multilingual representation. This is very strong assumption, because then just finding the representations on finding good probe for one language, we can simply parse the sentences in another language without any tuning to that language. There is also, if it's not true, we can try to make a bit weaker assumption, whether we, for instance, can have similar representation across languages, but first we need to apply some sort of information, some sort of transformation to really make them the same. And like, I think usually the used transformation was just rotation or orthogonal transformations of that space, when we can bring two clouds of embeddings in 2 languages together to get the same distribution. And we want to answer this question, those 2 questions actually, using our settings. So we are committed to our orthogonal probes, and we again probe for syntax, which is from universal dependencies in 9 languages, and also for word nets, which are also available for those 9 languages we chose. And we will make different assumptions about the representations across the languages. So firstly, we make like the weaker assumption, or I would say no assumption, that there are distributions of embeddings in different languages, but there can be completely different. So how to model it? We model it by just taking separate probes for each of the languages. So in our words of orthogonal probes, we have separate orthogonal transformation and separate scaling vector for each language. The second stronger assumption is that those distributions of embeddings are different, but are somehow similar. They're isomorphic to each other. So we can just rotate those clouds of embeddings across languages and then probe them in the same way. And we can model it also with orthogonal probes. In this way, we share scaling vector across languages, but have this language-specific orthogonal transformation. And with this approach, we can align those embedding distributions together. And if our results will be similar to the first setting, then we can say, yes, they are isomorphic because we are getting the same results. And the strongest assumption is that really this information, those embeddings are distributed uniformly across languages. So we can just find one distribution for one distribution from one language, and we can say that we can transform in the same way embeddings of English sentence and German sentence, for instance, and we get similar accuracy. So this is, I call it uniformity assumption, and we model it by sharing all parts of the probe together. So if we can probe well for one language, we can the same way find the good results for another. And already I can go to results. Actually, we found that for those 9 languages we used, the isomorphity assumption holds. So we could get comparable performance in this setting and the first setting. For the third setting, so this assumption that those distributions are uniform, we also get good results, but it depends on the language you choose. So for typologically close languages, we found out that yes, those results are very similar to the first approach when we don't make any assumption about those distributions. But for more diverse languages, we drop significantly on the performance. So I will shortly show, I don't have much time to go into details, but I will shortly show the results. And in those results, in the tables, in the following slides, I will show the results for the first approach, and they're just differences between second and first, and third and first approach. So those be denoted by deltas. And if there be negative delta, we see that the performance drops. So for syntactic probe, we have those results I mentioned, that when we have the second approach, we don't see much deterioration, but when we want to fit the shared probe for all languages, we see that for some languages like Chinese, Arabic, we see more significant drop. And also when we aggregate the languages, we see that drop is more significant for non-Indo-European languages. For lexical probes, the results are similar, a bit different. Also, there were less data, so I would say that they're more noisy. But generally, yeah, maybe I will skip here. I have a digression, but I'll skip that. Generally, our finding was that this drop between this third, more strongest assumption and first one was correlated with typological similarity. So for more similar languages, the drop was small, and for more diverse, we had larger drop if we assumed that the languages are uniformly distributed. So it's just to summarize this work, found out that syntactic and lexical information were uniformly encoded across embedded representation to languages saying similar to English, but we can also exchange English to any close to English language. And for other languages, we could do orthogonal mapping of the embedding spaces to improve the results. So this is already often used technique to map the embeddings. So now I have a few more minutes, so maybe I will just shortly talk about current work in progress. So it's actually the work which is under review, but I think this is relevant to one of the questions where those methods can find applications. So here we wanted to look into one of the information which is harmful for the model. So in this case, bias, and especially the gender bias. So in gender bias is sort of signal, some sort of information which is acquired by the model, which is learned on large corpora, and generally it mostly appears when it sees sums of the words, which doesn't have grammatical gender, in the context which implies some gender of those words. So in many sentences, we will see male doctors, for instance, in the training corpora, and therefore the model could wrongly infer that all doctors are male. And yeah, it can be problematic because then we want to perform, for instance, language modeling and want to predict the pronoun for the word doctor, and we will see a strong preference toward male pronouns. Here we want to also have two kinds of informations, which we call gender bias, so this connection between words and gender, which can be not factual, so which mostly arises due to occurrences of specific words in specific contexts in the learning corpora. But we also have factual gender, which is in English, it's not as prevalent, but sometimes appears in pronouns when we have male pronouns and female pronouns. So based on those pronouns, we really have the factual gender information that he is male and she is female. And we actually want to probe for those two kinds of information. One would be gender bias, for instance, ask whether doctor is male, where models often can tell that, yeah, doctor is male, but it's not factual, it's just gender bias. But if you want to see if he is male, then we should get this information from the models. So we basically look into two causal associations in the based on coreference links. So we want to probe for the pronoun we want to use when the subject of the sentence is nurse or doctor, so female and male biased words respectively. On the other hand, we want to probe for noun based on the knowledge of the gender. And generally, we want to disentangle those two and get rid of this bias. So we don't want to associate nurse and doctor with specific gender, but we want to still keep the gender information which we have for pronouns she and he. So some partial results that we found out that we really in 3 probed models, we could somehow find those dimensions, which are called separately the bias and the factual information. There were also significant overlap between those two, which we also expected. But with those probes, we can try, and we currently are trying to get rid from the model, of this harmful gender bias, but still keep this factual information, which comes, for instance, from the pronouns. I'm almost out of time. I had also a short part about limitations of the probes, which is also very important. So maybe I will just say a few most important things. That I think the main problem with the probes is that probes tends to overfit to their data. And it's a problem with this approach, that we want to find out whether specific information is encoded in the model, but we still need to provide some data, and we also add some parameters to the models. And we are a bit in risk of the fact that the model don't really learn this property we ask the model for, but this small probe learns it. So actually there are a few examples to counter this effect. One was proposed by Hewitt and Liang, which proposed for probing for tasks similar to linguistic tasks. So in their case, it was classification part of speech tag, but they shuffled the labels. So they sampled some artificial labels for the words. And for some sort of the probes, also they could get very high accuracy, which is a big pushback to probing, because if you want to know that linguistic knowledge is encoded in the model, but we can probe for any random knowledge, that means that our experience wasn't good, because we just added enough capacity to the model to learn effectively this new task. So this work was, I would say, influenced others, and I think in a good way to also include some controls of the probes. So this is also why, before I talked a bit at the beginning of the presentation, that we randomly sample the trees, and this is in our setting. This plays a role of this control task. So we randomly sample the trees and assign them to the sentence and see whether we can also probe for those. And we computed the average accuracy for all the tasks and subtracted this this accuracy for those randomly sampled trees. We call it selectivity, which is in line of also Hewitt and Liang work. And we saw that this selectivity is quite high. So we get, like, averagely, we can get correlations for linguistic information, linguistic structures on the level about 0.8, while for randomly generated tree 0.2, so which translates to about 0.6, even a bit higher selectivity if we subtract one from the another. And also, what is argument for using orthogonal probes is that with orthogonal probes, the selectivity is higher. It is because adding this orthogonal constraints to the probe that we use also a bit regularizes the probe, so it makes it less prone to memorize the randomly selected trees. There are a few more points of limitations of the probing. I would just maybe if there be questions about it, we can talk it further, but I want to take much more time. There is recently a very good paper for Jonathan Belinkov, which lists 5 main limitations of the probing, and I think those are sort of checklists what we should consider in doing any of the probing experiments. So I would say that there are limitations, but there are also ways to overcome them. And just to close, just reference lists. I didn't put like all the list of the different papers, just printed maybe some most relevant 2 papers: analysis methods in neural language processing, which already is 4 years old, I think, from Jonathan Belinkov, James Glass. There's also primer or invertology, which is invertology is also often a bit, I'd say maybe mocking name of this field because it's mostly deals with birds. So it's like science of birdology, which also summarizes some many more methods that I talked here about. So it's also worth to read. And there are also books. So very recent explainable natural language processing for under Sogart. Also books from ÚFAL. And more broad, generally in machine learning from Christoph Molnar. I think most of those books and papers are available online, and this explainable NLP, it's in our office, so you can drop by and borrow it. So thank you for your attention. Just for summary, so I described this method of orthogonal probes and generally other works which comes from them. And I think they offer very interesting insight into information that is encoded in language models. Also that with this methodology, we can find the relationship or study those relationship between encoding of both different linguistic features, but also different languages. And it is opportunity, but with some, I think, drawbacks to control the information stored. So in this case, for instance, gender bias, which is harmful to the models, which can be found in the model, and there are many papers which show that it's a problem, and also there are a few approaches which try to mitigate it. So once again, thank you for your attention, and I'm ready to answer any questions you have.
Well, Tomasz, thank you very much